So Chapter 5 deals with stereoisomerism and handedness or chirality. So just an overview, there's isomers. We've seen constitutional isomers, which have the same formula but are connected differently. And the order of connectivity of atoms is important there. And then we have stereoisomers, which have the same molecular formula and constitution. So they're put together the same, but their different spatial arrangement of atoms is present. So in 3D space, they are a little bit different than a constitutional isomer, which is connected totally differently. In pharmaceuticals, we see slight differences in the 3D spatial arrangement, and those differences can make the difference between a targeted treatment and undesired side effects. Carbon-carbon bonds that are constrained in a cyclic structure cannot freely rotate. Although the two molecules below have the same connectivity, they're not identical. So here we have CH3s on the same side of the ring. Here they're on opposite sides of the ring. And on this double bond, we see the same thing. These are on the same side. These are on the opposite sides. With rings and with carbon-carbon double bonds, we have a cis-trans notation that's used to distinguish between the stereoisomers. If you have something that is cis, this refers to identical groups on the same side of the ring. Or double bond. And for trans, it's identical groups on the opposite sides of the ring or double bond. So in this case, the CH3s are on the same half of the ring. So this is cis. This is trans. So this would be a cis 1,2-dimethyl cyclohexane. And this is trans 1,2-dimethyl cyclohexane. So something that is chiral is an object that is not identical to its mirror image. These are non-chiral because they are identical to their mirror image. So we have a wine glass, a bottle, the letter I. These sunglasses here are non-chiral. These are not identical to their mirror images. So your left hand is different from your right hand. Even though there are mirror images of each other, they are chiral, so they're not the same. Same with your feet and with the letter E. We have amino acids, sugars, and nucleotides, which can also be chiral molecules. So something that is superimposable, these are objects that can stack on top of each other, or they're identical. These sunglasses, you can stack the mirror image of it on top of itself, and it would be identical, so that is superimposable. But these ones here, if you take the mirror image of these sunglasses and you flip them over, you would have one of the sunglasses here. This one would be the shaded one, and then you have the unshaded one, and you could not stack those on top of each other, so these ones are chiral, and these are non-superimposable. So all of these things here are superimposable. And these are non-superimposable. So there's no way that you can stack your two hands on top of each other and have them match up correctly because they're mirror images of each other. Chirality will most often occur in compounds when there's a carbon atom that is bonded to 4 unique groups of atoms. So here we see an OH, H-methyl ethyl. These are all different groups. So it can have a mirror image of itself that is a stereoisomer of that. So this is just a 3D version of that. So the molecules below also have 4 unique groups. What's not shown here is a hydrogen. So this is the center of chirality here. This OH is bonded to a CH2CH3. This one is CH2CH2CH3. So these are 2 different groups. OH is a different group and the hydrogen is different. there's a center of chirality here, and this one is different here. So this carbon is different than this carbon. We have a CH2 versus a CH. So those are all the centers of chirality. Identify all of the chirality centers, if any, in the following molecules. If you look at this first carbon here, there's a carbon bonded to a CH3 and a CH3. Since these two groups are the same, this is not a chiral center. This group, though, is different than these two. So this is a chiral center, and this is a chiral center. So just because stereochemistry is shown does not make it a chiral center. And likewise, if it's not shown, that does not mean that it is not a chiral center. This group is different here. This is different. And these do not count because it's an sp2. sp2 cannot be chiral. And the same goes for sp. This OH is different from this one, so those are both chiral centers. And when we look at this OH right here, we have CH2 versus a CH2, so you just want to keep going around the ring. This is the same as this, and this is the same carbon literally, so this is not a chiral center. We can have something called enantiomers, and these are two molecules that are mirror images of each other, but they're not identical and non-superimposable. If we have this molecule here, this is the mirror image. If you can imagine picking that up and turning it around, there's not a way where those two can stack up on top of each other, just like your hands. These are two enantiomers. This is R carbone, so they differ in this center right here. This is the R and this is the S, and we'll get to what those mean just a little bit later. This structure is what you might find in spearmint. So that might be used in gum or mint ice cream. But if you have S-carbone, you're adding the wrong enantiomer. This is caraway seeds. So if you like rye bread, that's where you would see that. But if you were looking to make mint chocolate ice cream and you added S-carbone, that would probably be a not very appetizing ice cream. To draw an enantiomer, there is two ways that I can think of to do this. The first is to draw your mirrored plane. Draw your mirrored plane and draw the reflection of the structure. The other way is to just draw the structure as it is and flip to stereochemistry. This goes from being a wedge to being a dash. Once you've drawn an enantiomer, what we need to do next is to figure out how they are different. So you saw earlier with the carbone, we had R and S. So we have to designate these things as R and S. So these are both the structure of 2-bromobutane. In one structure, the bromine is coming forward, and the other one it's going back. So in 3D space, these are different from each other, which makes them stereoisomers. And we know that they're enantiomers of each other also. So the Cahn-Ingold-Prelog system is used to identify the differences between the two, because even though they're enantiomers, we know that they're not identical, so they can't have identical names. We use atomic numbers to prioritize the 4 groups attached to the chirality center. So 1 goes to the highest, and 4 goes to the lowest. Then you arrange the molecule in space so that the lowest priority group faces away from you. Count the group priorities 1, 2, 3 to determine whether the order progresses in a clockwise or a counterclockwise direction. And for clockwise, you get R, and for counterclockwise, it is S. What do these rules mean exactly? If we're using this to prioritize, we're looking at the groups. The one with the highest atomic number is going to be 1. So between bromine, carbon, carbon, bromine has the highest number, this has the lowest, And then we have a C that's bonded to a C, or a C bonded to 3 H's. This one has a higher priority, so this becomes 2. This is 3. And then we draw a circle around 1, 2, 3. We ignore 4. So this would be R. So we would make this R2-bromobutane. This is a different example, so we're going to do the same thing. We have using atomic number, we're going to prioritize. So the carbon of chirality here is on this one. Bromine is 1. We have a carbon with 3 H's versus a carbon with an OH. So this is 2. This is 3. The lowest priority group is away from you. So H is back, which is what we want. So now we just count the priorities. 1, 2, 3. This one is going in the counterclockwise direction, so this is S. If 4 is not pointing away from us, what we can do is you can either redraw it, so you can redraw it by flipping these two around and flipping these two around. So it's kind of like just if you picked it up off of the page and flipped it over like a pancake. Then the H becomes back, these two things stay in the plane, and then you have the chlorine, and then you can determine the stereochemistry. So this would be 1, 2, 3. This is 4. This would be S. All right, the other method is to determine as usual. And then take the opposite. So for this, we would just determine it as you normally would. So this is 1, 2, 3, 4. And as it's drawn, it would be R. But we have to take the opposite of that because H is in the wrong direction. So this becomes S. Either method works for you. You can do that. That's what you can do when H is coming out of the page. If H is in the plane, then you have to redraw it. So you have to flip both things again. So what I usually do is I flip the H for the smallest group with the one that is dashed. And then this one gets flipped around also. So when I redraw, my I is now in the plane, H is hashed, CH3 is wedged, and then the BR is now in the plane. So then now you can determine the stereochemistry. 4 is where it should be. So iodine is 1, 2, this is 3. So we have counterclockwise is S. So when you need to figure out the stereochemistry, sometimes you have to analyze the numbers one layer at a time. So this is 4, this is 1, and here we have a carbon with H's, CHH. That is a tie. So then we have to go to the next atom out. This is a C bonded to a C. This one is C bonded to a C and an H. And another H. So when we go to the second layer, this side has the higher priority. So this would be 2, and this is 3. So we're not looking at the total size of the group coming off of this carbon, but it's the next atom of connection. So for this one here, this is 4, 1. This is a C bonded to an O and an H and an H. This is C, C, C. So even though collectively, if you added all these C's up, that's bigger than an OHH, we're looking at the first atom of connection. So this becomes 2. This is 3. This is also S. This is just continued. If you have a carbon double bond, that counts for 2 oxygen atoms. So it's like it's bonded to a C and 2 O's. Same thing with triple bonds. This triple bond counts as C bonded to 3 C's. And this is 3 bonded to 3 C's, but this C is only bonded to a C and an HH. So this would be 1, 2, 3. All right, and this one right here, we have 1. Well, this is bonded to 3 carbons. This is bonded to 2 carbons, so this is 3. So determine the stereochemistry for these. This is a Parkinson's drug. So this is the chirality center. This is 1, 2. We have carbon to 3 oxygens. This is 3, which is just a carbon to 2 carbons. And our hydrogen is in the wrong direction. So I'm just going to do it as I normally would. This is 1, 2, 3. So that would be R, but we have to take the opposite, so that's S. This is the structure of methamphetamine. This is 1, 2, 3. My hydrogen is in the right spot. So this is S. It seems like every molecule here is S. That was not intentional. For a practice problem, assign the stereochemistry to the indicated centers. So this one here is 1, 2, 3. This one is R. This one here is 1, 3. This one would be S, but the H is the wrong way, so this one's R. 1, 2, 3. This one would be R, but that becomes S. And if you want it for practice, you can do the rest of them around the ring. So now we can tie it into the name. So earlier we found this name to be R2-bromobutane. So we'd write the R out front in parentheses. This is the enantiomer of that one, so it has to be S2-bromobutane. And the stereochemistry here, this is 1, 2, 3. This is R. This is 1, 2, 3. This would be R, but the hydrogen is forward, so that becomes S. So this is 3-methyl 2-pentanol. At 2, we have R, and at 3, it's S. So that's how we would name that one. Most drugs have a chiral center that has one form that is more potent. One enantiomer will bind better than its enantiomer, and it will elicit different responses. So we have S-ibuprofen and R-ibuprofen. This is the active form. This is inactive. But companies actually sell it as a mixture, and they think that the R-ibuprofen converts in the body to the S-ibuprofen. There's a high cost associated with separating enantiomers, so as long as it's not a harmful form, they will sell it as a mixture. Okay, so we have R-penicillamine and S-penicillamine. One is toxic, the other treats arthritis. We have S-timolol, that treats angina. The other one treats glaucoma. And then naproxen is an anti-inflammatory in the S, and it is toxic in the R form. So if it's the wrong enantiomer, it can't bind to the pocket properly. We can see the wrong enantiomer here. Those things do not fit where they're supposed to.